In this video, we will look at how conductors respond to an electric field. And after we've learned a bit about that, we'll look at how we can take advantage of this and use it in conjunction with Gauss's law. Imagine a block of conductor which we expose to an electric field. How does the conductor respond to the electric field? Well, we know that the electrons in the conductor are free to move in the body of the conductor. And we also know that electrons are negative charges. Using the equation F equals EQ, we can see that the negatively charged electrons will start to feel a force in the direction opposite to the electric field. As a result, they will start to pile up on the left-hand side. Here we're representing the electron excess as red shading. But of course, since the conductor started off as neutral, if the left-hand side becomes negatively charged, then there must be a positive charge somewhere else. In this case, if we think of the excess positive charge as also feeling a force from the electric field, it makes sense that it would pile up on the right-hand side. So we can see that the conductor, in response to being exposed to this external electric field, has become polarized. But the charges in the conductor not only experience the external electric field, they also create their own electric field. Inside the conductor, we can see that this electric field will point from positive green charges to the negative red charges. Let's denote this internal field with some blue field lines. Initially, when there's only a little bit of red negative charge on the left and a little bit of positive green charge on the right, this internal field is not very strong. And so the dominant field inside the conductor is still the external orange field. In response to that external orange field, the electrons continue to move to the left, piling up on the left-hand side, and leaving more and more positive charge on the right-hand side. And as a result, the internal field gets stronger and stronger. As the internal field gets stronger, the combination of the internal and external fields inside the conductor gets weaker because they're canceling out. Eventually, the internal field gets strong enough that it perfectly cancels out the external field, leaving us with a total field of 0 inside the conductor. So we are left with this situation where the external field is still there outside the conductor, but inside the conductor, the external field and internal field cancel out. We can see that the external field is consistent with the charges we have left. These negative charges on the left, field lines are heading towards them. These positive charges on the right, field lines are heading away from them. But inside, the external and internal fields cancel out. This process of polarizing the conductor and the internal field building up to cancel the external field happens incredibly fast on the scale of nanoseconds. So as long as your conductor is in equilibrium, that is, the charges in the conductor are no longer moving, then we assume that you've reached that state of equilibrium where the internal and external fields have canceled in the body of the conductor. Now, if you had a hollow space inside the conductor, things could be different. We shall investigate that a bit further. But in the body of the conductor, in the material of the conductor, we see that the charges rearrange in such a way as to cancel out any external fields. Let's consider a scenario where we have a green point charge near a blue conducting sphere. In response to the electric field lines of the point charge, we expect the electrons in the conducting sphere to move. We expect the negative electrons to crowd towards the side of the sphere closest to the point charge, while the positive charges are repelled further away and are spread over the far side of the sphere. One thing to notice is that for three-dimensional conductors, charges always reside on the surface. So here, the negative charges gather on the left surface and the positive charges gather on the right surface In between, in the material of the conductor, the field is zero, and so is the charge. As a result, even if you put an excess charge on a conductor, since it all goes to the surface, you never have a volume charge density with a conductor, but only a surface charge density. How much charge gathers on the left side and on the right side? In this case, there's not much we can say. We know from physical considerations that if we were to move this point charge further away, the amount of polarization on the conductor would decrease. There are tools by which we can mathematically calculate how much that excess charge is, the polarization charge is. But for now, there's not much we can say. But now let's consider a slightly different scenario. Let's consider a conducting sphere with a cavity inside, that is, a hollow space inside. Into this hollow space, we place a point charge. In this case, let's say -5 coulombs. Predictably, the charges of the conducting sphere respond. The electrons will be repelled by the point charge in the cavity and move to the outer surface. Similarly, the positive charges of the conductor will move to the inner surface of the cavity. So in this scenario, is there anything we can say about how much charge there is on the inner surface and how much charge there is on the outer surface? Well, if the conducting sphere started out neutral, then however much charge is on the outer surface must exactly cancel the charge on the inner surface. But still, how much is it? Does it depend on the size of the sphere? If the sphere gets really large and the cavity also gets really large, does that mean that the amount of charge on the inner surface will go down? It turns out, unlike the case where the point charge was external to the conductor, in this case, we can actually use Gauss's law to get to an answer. Of course, to apply Gauss's law, we first need to draw a Gaussian surface. Here, I've drawn the Gaussian surface in purple, and you can see that I've placed it right in the material of the conductor. Gauss's law tells us that the electric flux through the Gaussian surface over the entire Gaussian surface will be equal to the charge enclosed divided by epsilon naught. But flux is the integral of E dot dA. And we know that the place where we have put our Gaussian surface in the material of the conductor, that at that spot, there is no electric field. So this left-hand side must be zero. That tells us that the charge enclosed must be zero. But where is the charge enclosed by the Gaussian surface? There are two contributions. There is the charge on the inner surface of the cavity. That certainly is inside the Gaussian surface. And there is the point charge. So the sum of these two charges must be zero. But we know how much the point charge in the cavity is. The point charge is -5 coulombs. And so the charge on the inner surface of the conductor must be +5 coulombs. If we started out with a neutral conductor, then the charge on the outer surface must again be -5 coulombs because charge is conserved. So if the conductor initially had zero charge on the material of the conductor, then afterwards, even when it's polarized, the charges have to add up to zero. So you can see how here, by taking advantage of the fact that conductors have zero field inside them, we can actually find out how much the charge is on various surfaces of the conductor. Now, this doesn't tell us how that charge is distributed necessarily. We know that charges on a conductor have to be on the surface of the conductor, whether outer surface or inner surface, but they could be uniformly distributed or non-uniformly distributed. In this case, if I move the point charge in the cavity to one side, then of course the positive charges on the inner surface of the conductor will gather to that side because they're attracted to the negative charge. So there will be more on one side than the other, and it will be a non-uniform distribution. Interestingly, however, the charges on the outside of the conducting sphere, negative charges, will not be affected by the fact that the point charge has moved to one side. This is because they have no way of knowing it. In the region between the inner surface and the outer surface, the electric field is zero. and so there is no way of communicating that the charge is moved. Instead, the negative charges on the outer surface simply repel each other and spread out as much as they can on the surface. So on the outer surface, the negative charges would be evenly and uniformly distributed.